speech.
So very nice, very nice. Who did it, Annette?
Who did it? Lucia. Lucia did it, the video, yeah.
Congratulations to Lucia.
Yeah, we have now 1 year of Matemairacorana and a new year for Hildeberto also.
Very nice. So we are just on time. Should we start the second one? Okay. So it's a pleasure to introduce Professor Leonard Baker from Brigham Young University. He's going to speak about total collision in a four-body problem with Jacobi potential. Can you share your screen?
Okay, I think you can you hear me?
Yes.
Yep.
And let's see, let's start this screen share. Okay. I'm still just getting used to this. Okay, let me just, why is it so small? Okay, wait, let me see.
Professor Leonard, do you want to put in full screen? Is that?
Yeah, full screen. I'm just trying to figure out how to get it to work on your app with a full screen.
Maybe you have to share again. Maybe you have to put in full screen and after share.
Okay, maybe that's what I need to do. Maybe that's what happened. So let me try that.
You closed your camera.
Okay, got to close my camera. I did close my camera. I'm just trying to get my stop it, you silly thing. Okay, wait. I've got that. Let me just. Okay, I've stopped that. Let me now see if I can get my this to go full screen. That's what I'm missing right now.
Yeah.
Where did it go? Where is my full screen? I can't seem to find the crazy thing.
Yeah, your presenter. You can choose to share your full screen.
There we go. Okay. Okay, now let me just, now I remember where to find the crazy thing. Okay, let me try this again.
Okay. Camera, okay.
Okay, now where's that share screen again? Okay, I've got to somehow recapture my presentation. I missed that. Can you send, how do we do that again?
you can click, you know, downstairs where we are the microphone, the headphone, and the camera. You have a kind of notebook with a
oh, here we go. Okay, there we go. Let me find it. There we go. There we go. That's where I did that. Now let me go back over here.
Yeah, we can see your presentation.
All right, that look full screen, everybody?
It's black for me.
Uh-oh.
I don't know what happened. I see before.
So you're not seeing anything?
No, I see a black square.
Uh-oh. Okay.
Maybe you can present like this. We can.
Oh, wait. Let me try this. That work better?
You can see it now.
Okay.
Okay.
So let me see if I can make this window a little bit bigger. No. Stop it, you silly machine.
It's bigger now.
Okay. Nope, stop it, you silly machine. This way. Okay, we may just have to run with it this way. Is that okay, everybody?
Yeah, we can see.
I think you can see everything, and let me just.
Okay.
And I think I can advance the slide, so that'll work. Okay. Well, thank everybody. Grateful to have this opportunity to talk. This is joint work with Manueli Sandoprit and Christina Stoica. Manueli is at Laurier, and Christina's in the Ottawa area. So we're going to look at a four-body problem with two masses in a horizontal plane, the XY plane, and two masses on the vertical line. The two masses move in that horizontal plane symmetric to the origin, and the two masses in the vertical move opposite each other symmetrically with the origin. We're going to do this. We're going to use cylindrical coordinates to write out the Hamiltonian. And so a Hamiltonian for this model looks like this here, this H. We're eventually going to choose a Jacobi potential for this four-body problem. The thing to recognize about this, about the way we've set up these four bodies in three-dimensional space, is that we have this P sub theta, but there's no theta in the potential side. So we have the angular momentum for the two bodies moving in the horizontal plane, and angular momentum that is conserved. And so that P sub theta becomes a constant, and we have now this Hamiltonian here at the bottom. So to simplify things, we're going to set the masses of the horizontal bodies to be 1 and the masses of the vertical bodies to be alpha. And we're going to now take the Jacobi potential, the 1 over x squared. So this is not the Newtonian potential, but the one that's in between the weak and the strong force potential. And for notational purposes a little later on, we're going to write the potential in terms of two parts, the one with the angular momentum c, and then the one coming from the Jacobi potential. So we write this all out, and we get this nice Hamiltonian here. And if we combine the parts that are over r squared, we'll see that we have this part of the potential that has this 1 minus 4c squared in it. And as you can see, is if c gets bigger than 1/2, the character of the Hamiltonian changes. And we're going to see this play a role in the behavior of the solutions, and when we see C smaller or greater than 1/2. Now, interestingly enough, this Hamiltonian system, it has another integral, and you can compute this directly, that this J1 is another integral for this Hamiltonian system. So initially, the four-body problem was 3 degrees of freedom, but by having that angular momentum, we passed it down to 2 degrees of freedom, and now we have this integral J1. Now, interestingly, the integral J1 does depend upon the value of the Hamiltonian H. So, since we have the potential for a total collapse, we're going to now use McGehee coordinates. So we set up the system here to use McGehee coordinates to look at the total collapse and the total collision manifold. So standard procedure here to look at the McGehee coordinates. So we have our variables rho and v that will continue through. We have vector s and u that satisfy the standard relationships in terms of our weighted inner product given by the matrix M. And because we have those nice relations between those vectors u and s, we can write them in terms of an angle phi and u in terms of a scalar little u. And now in these coordinates, the energy relation, the Hamiltonian, now becomes this quantity here, rho squared h, equals a nice expression here. Now that v1 and v2 now become v1 hat and v2 hat, where the v1 carries the c2, the angular momentum, the horizontal bodies, and v2 has the alpha in it, the mass of the two vertical bodies. And you can see, of course, we have some issues here with phi equals pi halves, and in the v2 we have issues where phi equals 0, as well as pi halves. So what we do here, of course, we do a time change along with the, as part of the McGehee coordinates, and we get this the first order system here, 4 equations. And the thing you'll recognize here is that what turns out to be really nice here is if you look at the equation in V, that's looking an awful lot like the energy relation. And so what we do is we're going to use the energy relation to replace that. And then what you'll notice is that the first two equations only depend upon V and H, or V and rho, excuse me, V and rho. And then the second two equations only depend upon U and phi. So there's a nice splitting of the system of equations into two subsystems. This is where the, let me see what's on the next slide here. This is where the integral J1 comes in, because when you express the integral J1 in terms of the variables from the McGehee transform, rho, v, phi, and u, J1 now is strictly just in terms of rho and v, which goes along with the first two equations. And now there's also another integral J2 that goes along with the variables phi and u of the second subsystem. And now these two integrals are not completely unrelated to each other. If you look at the energy relation, and I've rewritten it down here at the bottom by splitting the part with u and v, I brought the v over to the other side. Well, this part right here is exactly J1, and the other part's exactly J2. So the values of the two integrals must equal each other at all times. Is basically we pulled apart the energy integral, or the energy relation. So just a little interpretation of the coordinates as we have them so far. So rho is, of course, is this weighted distance in terms of that inner product given by the matrix M. It's a size, it's a measure of the size of the rhombus, because the four bodies, you've got two in the horizontal and two on the vertical. They always form a rhombus at all times. And so rho gives a size of that rhombus. Of course, the rho equals 0 corresponding to total collision. The coordinate v is the rate of change of the log of rho, and that comes from looking at the first that difference equation in rho. You can solve it for the derivative of log rho equals v. The coordinate phi, that describes the shape of the rhombus, because we'll see in a second, phi is actually equal to the arctangent of this root alpha of z divided by r. And then u is the rate of change of phi, because d phi d tau was equal to u. So the coordinates r and z, so r was the distance of the horizontal body, since they're symmetric, is the distance of them both from the origin. Z, the symmetric bodies, and the vertical distance of z from those bodies from the origin, are related to rho and phi by these equations here. And so what we see here is that, of course, if rho goes to 0, you have total collapse or total collision. But if you have phi goes to 0, but rho stays positive, you have vertical bodies colliding, with the horizontal bodies not colliding. On the other hand, if you have phi goes to pi halves and rho is positive, you have the vertical bodies colliding, or the horizontal bodies colliding, but the vertical bodies are not colliding. So we have a good sense of what's happening here, as it typically happens with McGehee coordinates. So, of course, the one thing we don't have, if we go back here a second, is remember, we have problems with these functions v1 hat and v2 hat. They're not defined. They become singular at phi equals 0 and phi equals pi halves. So what we do, we want to extend the vector field to those two values. So we introduce this variable, this function w. We take our v2 hat, and we're going to multiply it by the square of sine of 2 phi. And the reason I put this in red is that we want to say, what does the w function look like? Well, here's what it looks like, and you see now that it is well defined at all values of phi. We're going to introduce a new variable w in terms to replace u and do a time change from tau to tau bar. And so now the energy relation becomes this quantity here. And I put this part here in blue to say what's happening with v1 hat. And v1 hat now also is well defined at phi equals 0, or actually pi halves, excuse me. And you'll notice something sneaky. You notice what's showing up here in the energy relation. There is J1. J1 shows up in the energy relation. But we expected this, right? Because J1 and J2 are just a splitting of the energy relation. So now when you go through all of that messy algebra for a few pages, you end up getting these equations here for the flow, or for the flow of this four-body problem. And now the first two equations are still essentially in rho and v, with this common phi here. And then you still have these two equations here. And so just I put this pair in blue, right? Realize that there really is no singularity there. That's well taken care of. So these equations here are well defined for phi from 0 to pi halves, including 0 and pi halves. So we now go back, look at the integral J1. It continues to be an integral for the first subsystem. And the level curves of J1 only depend upon h, not upon the mass parameter alpha, nor upon the angular momentum c. So here are the level curves of J1, visualized for three choices of h, for a negative value 0 and a positive value 1. And the thing to recognize here, here's the level curves for h equals -1, and they go up and they come back down. Here's v on the horizontal, h on the vertical. So this goes from rho equals 0 up and down back to rho equals 0. Over here you've got, so the way the flow goes on here for the first subsystem, it would go up on the right and then come down on the left. Here they would go down on the left and up on the right. Here on the vertical axis, you'd have the derivative of rho is 0. And then here for rho, or for h equals positive 1, on this side you have the flow going down. Here you have going up, and here you're going from the left up to the right. And so over here is we have J1 is negative. Here you have J1 is positive, and then the two lines that meet at the origin here is where J1 is 0. So here, the vertical line on here, this is where J1 is 0, J1 is negative. Here, all the curves have J1 is negative. So from right here, you can tell from this this integral here for the first subsystem that if you have h is 0 and J1 is 0, on the side where h is, or rho, the derivative of rho is 0, so rho is constant, you can never have a collision. So if you start with rho positive, you can never have a total collision. And also here, if you start with rho positive, it's always going to stay positive. You never have a total collision. So that leaves the possibilities of total collision. Of course, h is negative, with J1 always negative, or you take h0 and you take J1 negative, or you take h positive and you take J1 negative. So we know what the possibilities are now for total collision when they can occur, or when they may occur. Now the integral J2 for the subsystem with equations in phi and w, I always say we just basically replaced u with w. And of course we've got this little part in blue, that's really just J1, or the J2 value, because they're the same. But the thing to recognize here about the integral J2 is it only depends upon the values of alpha and c, but not upon h, because this is really just a constant sitting here. So, well, what are the values of, what are the integral curves of J2? Well, before we can do that, we have to talk about, because it depends upon alpha and c, this is where that c thing is going to come into play, because what happens, there are three regions. This region on here we're going to call R1, we're going to call this region R2, we're going to call this region R3, because depending upon where alpha and c is, we're going to get different topologies for the level curves of J2. Just so you know, where this curve branches off, the alpha value here is 16/15. So here are the level curves of J2. If you are in region R1, so that's C less than an absolute value less than 1/2, here are what the level curves of J2 look like. These are the solutions of that subsystem in phi and W. You notice there's a critical point for those level curves, and they do curves that make it all the way down to phi equals 0 and all the way up to phi equals pi halves. If you go into that region R2, where you have C, absolute value C bigger than 1/2 and alpha large, you have one critical point, looks like, and then another critical point, but you'll notice the curves don't make it up to the value of phi equals pi halves. If you take the alpha C pair in the region R3, there are no critical points, and the phi value, they don't make it up to pi halves. So here are the actual graphs of J1, their surfaces. This looks much better in my computer. I don't know why this is looking, well, at least my original version of these graphs look a little bit better. But here are the surfaces, and so you can see that's the, you know, you can see like that looks like a saddle point, and that is indeed what it is. Generically, it is a saddle point. There is a set of measures 0, which these critical points will be degenerate. So generically, they're non-degenerate. So in the region R1, you will get a generic non-degenerate saddle point in the region R1 for the level, or for the graph of J, or that should be a J2, by the way, that's a typo. And in R2, this is the graph of J2, you do get the saddle point there generically and the local minimum. And then in region R3, there is no critical point. Other thing too that we've proved here is that all of these critical values for the graph of J2 all occur, are all negative. They all occur for negative values. Okay, so now we can get to the total collision manifold. We obtain that, of course, by setting the rho equals 0 in the total energy or the energy relation, and that will give us this equation here. Where's it we got? We got W, phi, and J1, which will include V, and we also get the flow on the total collision manifold. The thing that, of course, is we typically see in these sort of Jacobian potentials is that the V variable is constant, and we've got the J1 variable, the J1 integral sitting there, and that's just equal to minus V over V squared over 2. So what happened? What did we get here? The topology and the flow on the total collision manifold depends upon which region the pair alpha C belongs to. If you're in region R1, then you get the traditional thing you typically see is a sphere. Topologically, the total collision manifold is a sphere with 4 points missing. But because the derivative of V is 0, your solutions are always moving from left to right. If you're in region R2, alpha C is in R2. I should mention here, there actually are 2 lines of degenerate equilibria. These correspond, this side here corresponds to double collisions of the vertical bodies. That's 0 corresponds to the angle phi equals 0. Over here you have double collisions of the horizontal bodies. Pi halves corresponds to phi equals pi halves. Now, when we get to R or alpha C and R2, now the topology has changed. We now have a sphere, topological sphere with 2 points missing, a union, a disjoint union of a line. That is now the topology of the total collision manifold. And when we get into R3, we still have a 2 sphere with 2 points missing with the union of a disjoint line. So these 2 cases here occur when the absolute value C is greater than 1/2. But now the flow on these is between these 2 cases, R2 and R3, is determined by alpha, if it's in R2 or R3. When you're in R2, there are the appearance of 2 extra equilibria, and these correspond to centers surrounded by periodic orbits. And in R3, there are no periodic, or there are no equilibria. So there are, and we get all of this. We actually got these using the Poincare-Hopf theorem in surgery. We remove the lines of equilibria, sew them up, put centers at the tops of these things, and use Poincare-Hopf theorem to get the stability of the equilibria on the collision manifolds. Now, you can do the linearization as well and get the dimensions of the stable and unstable manifold, but these also follow from the level curves of J2. So, and with all this information now, we can now start talking about things like homographic orbits. And with those homographic orbits, we just now plug those into the first subsystem. We want to know, how does rho evolve with those homographic orbits? Now, I wrote down E minus and E plus. Those apply to all those equilibria on the collision manifold, with 1 or 2 down here as well. If you take negative energy, they will go from the E pluses, the ones with V positive, and they will go to their corresponding E minus, and so you will get homoclinic orbits, which are homographic. So that's where the angle phi stays constant. That's the homographic orbits. So if we go back, you will have from E plus, there will be a homographic orbit going to E minus. From E1 plus, there'll be a homographic orbit going to E1 minus. E2 plus, there'll be a homographic orbit going to E2 minus. And that's what this picture's saying. Now, if you go to H equals 0, they, of course, will no longer be, or excuse me, heteroclinic is the term I should be saying here. Well, not there yet. So yeah, these would be heteroclinic. Okay. Now, if you do H equals 0, they'll no longer connect to their corresponding symmetric equilibria on the collision manifold. And same thing for H positive. Now, so as I mentioned in the abstract, we'll talk about what are called oscillatory orbits. And these are coming from these periodic orbits that are surrounding here in the region R2. When alpha and C are in the region R2, you've got these periodic orbits around E2 plus and around E2 minus, right? Because for the integral J2, we've got these periodic orbits for the subsystem within phi and W. And so when you put together the solutions from the integral J2 and the solutions from the integral J1, so what happens is if you take the energy, or if you take H negative, so you have these curves from the integral J1, backward in time, you're going to limit onto these periodic orbits here. Forward in time, you're going to limit onto the periodic orbits here. And so you're going to get a cylinder, a topological cylinder. And so these are solutions not limiting onto an equilibrium, but you're going to get this angle phi, which is oscillating here, and it's going to oscillate as it limits to a total collision orbit. So the angle phi, which measures the shape of the rhombus, doesn't have a definitive limit, but it oscillates the whole time as it approaches collision, total collision. So this is backward in time, but as it approaches, so as it ejects, it ejected from an oscillatory angle, so its rhombus shape was oscillating, and as it approaches total collision, it also oscillates. So that's what I'm trying to draw here in this my handcrafted picture here. So as it ejects, but as it comes down now here and approaches total collision, it is oscillating in this angle phi. Now, we can do the same thing with H equals 0, but now, of course, it would simply just eject and it wouldn't come back, but also there'd be ones coming in from the bottom that would approach total collision with oscillating angle phi. And then the same thing for H positive. They would eject, then also be coming in. All right, thank you. I'm just glad my voice held out long. I've been having a little bit of a cough and a cold and laryngitis.
Many thanks for your talk, Leonard. Now we are able to hear you perfectly.
Okay, excellent.
We are open for questions. Let's see. Well, Annette, do you want to make any announcements for next time? No? Okay, so let's thank the Professor Leonard again. So when is going to be next meeting? 2 weeks?
30 with Vivinha.
Okay.
I stopped to recording to take the